So let's switch our chapter. Let me see if there is any question before we go. Okay, yeah, very good. To a very interesting chapter of algebra and number theory. I know that many of you guys have taken this course, in high school probably. Many of you might have good memories with this course, or many of you might not really like this algebra and number theory at all. So the good news for you is that I'm going to explain this in a very different way, because we are going to use, we need this knowledge for algebra and number theory to better understand different algorithms. So it is very crucial for us to have a very good background, at least a deep understanding of how things are going on with algebra. So algebra itself is a very, abstract course. There is not much of immediate application when you unfortunately study the course. But what I would try to do in this chapter is to turn it into a little bit more fun. I'll give you tons of examples to make, because, talking about abstract things is already hard to imagine. So unlike most of the algebra books and number theory books, I'll give you tons of examples. So we would start to see examples, and then we would generalize and understand the concept out of those examples. So this would be our method of teaching for this chapter. So given that, let me choose a good color. Okay, good. We are talking about abstract algebra. So, okay. So, if you remember, in algebra, one of the most important things that they discuss, and we're using it in our daily lives, is a group. So what is a group? So this is the question that we have in our mind. So to really understand this, from a completely different perspective, I always try to, again, start with example. Suppose we are, living in a different planet, because I want to give you a different perspective. And then, a day in this planet takes only 7 hours. So you're talking a clock that starts from 0, then 1, then 2, then 3, 4, 5, 6, and then we get back to 0, which is 7. In our planet, it is 24 hours, we have 12, and then we're good to go with that. But now it is just 7 hours. So I chose this number because I want you to see a new example and correlate that with what we have in our planet Earth. So what we are going to discuss is something called clock arithmetics. So it is going to be clock okay. So let's just start with some examples. So let me draw the time. 1, 2, 3, 4, 5, and then 6. So in the clock arithmetic, something is very interesting. Suppose that we are at 3 o'clock. Let's say we don't care about the minute. And then I ask you that, what would be 5 hours after when the time is 3? So what you would do to do that math is that you add the time, right? 1, 2, 3, 4, 5. You end up here. So in 5 hours, you end up to be in clock 1, right? When you add that 5 hours after clock 3. Let's go through another example. Suppose that, let me draw this clock again. Five and 6. So now suppose I am at 4 o'clock and I ask you what happens if I add 3 hours to that? So adding 3 hours, 1, 2, 3, we go back to 0, right? So interesting. So just adding 3 hours, I go back to 0. We can do also subtraction as much as we do addition. So if I again draw this one, right? And let's say we are at time 1. So 1 minus, if I do 3 hours. One thing that you can always remember in addition, thing that you can always write subscription just like addition. So I can say 1 plus minus 3, right? So this way means that I don't have to have another operation called subtraction. If I have just addition, I'm good to go. I can just use addition plus minus some number, and I can achieve the same thing that I wanted to do. So that's why in a lot of groups, we always talk about addition. We don't talk about subtraction. So if I'm at time 1 and I subtract 3 hours, that would be 1, 2, and 3. So I end up by 5, right? So I go this way. So then I go back to the time 5, right? So seeing these examples that I've just gave over here, so the clock is something that is very tangible for you guys. You use it every day, and we saw this one. So believe it or not, this has a lot to do with the concept that we use in abstract algebra, and it's called modular arithmetic. So, okay. So modular arithmetic, for example, we have integers mod 7. This is the clock that we are talking about. So which brings us to some discussion. What are the integers? Remember that the integers, we always show them with the set Z with double stroke over here. And this is a set of all numbers from negative to 0 to 1 and 2 and all the way to infinity, right? So this is a set of all integers that, remember, we used Z to denote them. And then when we apply this modular operation, we are going to name this group Z7, which denotes that, any number that we take from this set, we apply mod 7. Mod 7 would return the remainder when you divide that number integer, whatever you take, to 7. So when you take the remainder, you see that you always end up with a finite set of numbers, 2, 3, 4, 5, and 6, right? So do you see the relationship over here with this clock that we just made together? So the clocks are something that we've been working on for many years, and it was very familiar. But when we want to move to, a little bit more scientific discussion, we would just discuss them as modular arithmetic. And you see that it is nothing but just taking, if you take any integer from the set, any number, small or huge, if you divide that to 7, you compute the remainder, it is going to be always some value from here. So now you see that what we've been discussing over here has something to do with this modular operation and this clock arithmetic that we've been doing there, right? Let me add another page. So let's, now that we have seen these two, a set of integers, we know that they are a group, this modular arithmetic or clock arithmetic are a group. Let's see what do we mean by that they are a group, right? So we are going to define, to answer the question from the previous slide, that what is a group. To answer that, let's compare these two things together. So remember we had a clock, 0, 1, 2, 3, 4, 5, and 6. And in the previous example, we saw that this is equivalent of something we have in Z7 modular arithmetic, right? And imagine that I want to compare that one with the set of integers that we have, that, we always use them to add minus number and do all those sort of, computation on daily basis. So looking at these two sets, the first thing that I see is that they have some elements, right? So the elements over here are 0, they're finite, 2, 3, 4, 5, and 6. And over here, we have infinite amount of elements. So we can have 1, 2, and 2 infinity, right? So the first thing that we see is that one of them is finite. So it is finite, right? And then the other one is infinite, right? Then we talk about, adding, if you're at 1 o'clock, we add 2 more hours and so on and so forth. So we were talking about some operation. So in both these sets, we have operation plus addition, right? So we can take 2 elements from any of these things. So we said that I'm at clock 1, I add like 2 hours, I end up by 3. I take an integer 4 and I add 2. That addition is defined in this sets. A lot of this, it just comes for granted, but when we talk about different sets, then things would start to make sense, and you will see that the operation doesn't have to be always plus. And then we have another thing that they have in common in both this group is closure. In closure, what we always discuss is that any operation, if you take any element and then you do this operation on them, you always end up with some element in the same set. That is very important. So we say that for any A and B that you take from Z7, if you do A plus B, of course, mod 7, this would be an element in Z7, right? So this is very important. And over here, the case of integers, this is already obvious, right? If you take any 2 integers, you add them together, or if you take any integer and then you subtract it to another integer b over here, so you always end up with another integer. You don't get into some float value. Integers are always integers. And that is a thing that is important. And then there is another property that is very important, and that is something called identity element. What is that identity element? An identity element is an element that has no effect. What does that mean? In addition, that identity element is 0. So we say, for any integer e in Z7 that you choose, if you do a plus 0, you always get 0. You always get a. So this element has no effect. That is very important. And for addition, when the operation is addition, that element is always 0. And when operation is multiplication, that identity element is always 1, because if you multiply any number to 1 is itself, so that is identity element. So we have something called inverses. So remember that inverses is a value that when you add that value up to itself, you would end up to the identity element. In the clock arithmetic up here, in the previous page, we discussed an example that when you're at 3 or 4 o'clock, you add 3 more, you end up to 0, which 0 was our identity element. So 3 and 4 are inverse of each other, right? So we say that if you add 3 plus 4, this would become 0 mod 7, right? So we normally show inverses of any element, there is the element A in Z7. We show the inverse of A as A minus 1. It is not A to the power minus 1. This means that inverse of A. Looking into the set of values in Z, how about that? How do we find the inverses? For any A in Z, the set of all integers, the inverse of that value is the minus of that. So if I do A plus minus A, I always get 0, right? So the inverse of any element is just minus A, right? So because I add that, so the inverse of 3 is minus 3. The inverse of, 8 is minus 8, right? Because if you do 3 plus minus 3, you get to 0, right? Which is the identity element. And the next property that you will see that we have is associative property. And the associative property says that if you want to do A plus B plus C, no matter how you would parenthesize and spread the computation first or prioritize one to the other one, you always have the same result. So plus B plus C. Okay. So most of these things are trivial, but there are some groups that you cannot do this. Based on different operation that those groups they've got. You cannot have this associated property. And we know that this exists for the set of integer Z. But you might ask yourself that why are we talking about these things? Why are these things are important? It is to give you a little bit of background why this groups and things became important. We need to look back into the time in 1100. Around the year 1100, we had different scientists that they were working on different things, solving equations and things like that. At that time, we could solve, quadratic, cubic equations, but we didn't know how to solve, equations of degree 4, 5, and so on and so forth. Math didn't come overnight. It took years of hard working to get to know how to solve those higher degree polynomials. Remember when you want to solve a polynomial, we say that some f of x, some polynomial equal to 0, find those root values that make this polynomial or equation to become 0. So finding those integer or whatever values that cause setting that to x would make the equation to be 0 is what we call solving the equation. We didn't know how to solve those things. But what some scientists like Euler, for example, and Gaussian, they were working on some different things. Euclid was working on different shapes, and then Euler was working on number theory. Gauss was working on number theory and so on and so forth. What Euler found was that if there is a way that we can generalize, the concept, of different shapes, if they form a group, and if numbers like integers that, as you could see, they can form a group, then if we find how to solve, one equation, then we can use the same technique to solve, different equations on number theory. We can use the same technique to solve different things on shapes, geometry, and so on and so forth. So that was the intuition that they said that, let's sit down and make a concept of groups that if geometry, shapes, number theory, and any arithmetic, modular or non-modular, works, then, if somebody finds some breakthrough result in geometry, then we can apply that exact, idea into numbers. So we don't have to basically reinvent the wheel, and therefore, life would become easier. So I just give you an example of, some of these things that it took them years of hard working to sort out this specific properties so that they can start to form groups. Let me add another page to keep things neat. So now that we have seen some of these properties, and actually there are very more properties out there, but in order to form a group, it has to be very general and it cover the set of all possible shapes and things. So we don't want to make it very narrowed down. So we want it to be as generic as possible. So let me give you a formal definition, and then we see with an example how is it so. So we are talking about groups. So a group is a formal definition. So a group, as we discussed in the previous thing, has a set of elements. That is the first thing that we saw. The second thing that we saw was that a group, when you have the elements, you want to do some operation with them. So it has an operation. So normally we would use asterisks for operation to be very generic, but you can always imagine that asterisk is plus or multiplication and so on and so forth. Okay. And then another property that has is closed under this operation. So it is closed under this as whatever operation we define over here. So that means that if X and Y are in group G, then X asterisk Y would also become something in group G, right? So normally we denote a group with the capital letters. So we use G because, well, G is the initial letter for group, so it is easy to remember. So the next thing that we want to do is identity element. So we said that we normally show it with E. So identity element. So it was an element that if you take any Y, you multiply it or asterisk E, you get this Y back, right? And then we have inverses. So the inverse of an element is that X, you do this asterisk operation to X minus 1, and then the inverse of X, you are supposed to get back to E. And then the last one is associative. So we said that if you do A asterisk B asterisk C, it should be the same as A asterisk B asterisk C, right? So that the way that you choose the operations, the variables shouldn't really affect. But you may ask yourself for many years of study algebra, why these rules? Why not more? Why not less? Who says that this should be there? You always maybe wonder that why do we need to have this many to form a group? So, well, let's answer that question. So why only these rules? So let me start with an example. Suppose that I, let me do example, and then over here I want to write down the property that you use. Okay. Suppose that I ask you to solve this simple equation, x plus 3 equals to 5, okay? that is my question. And this is very simple. You can just answer it right away. But before we do answer that quickly, that is not the purpose of this small test. The intuition is to understand why do we need these rules in order to solve this polynomial. So the first thing first is that we see that we are adding some integer and some variable. So it means that so integers are closed under addition, because when you add two integers, you expect to receive x to be some integer. You cannot x to be some float value, and then you add them all together to get an integer. So the first thing that we see from over here is that these values are closed. So when you start to solve this equation, I want to go very easy and see the concept. So the first part is that we want to get rid of this 3 on the left-hand side. So what we try to do is to find the inverse of 3, which is -3, to cancel this effect of 3, right? So we get 5 plus -3. So what we have used is inverses, right? So the first thing was that it is closed under operation, and now we are using inverses in order for us to be able to solve this, right? So in order to solve this thing, so we would get x plus 3 from this side plus -3. We get, if we add these two things together, we get 2, which again we get integers are closed under plus, right? Whenever you add two integers, you get another integer. That is a property that we use. So that now that you could see over here, we need to, change the parentheses. That means that we need to use associative rule, be able to solve this one. So we have to do x plus 3 plus -3, right, equals to 2. And we could not achieve this if we didn't have associative, right? So we have to add this one to the game. So adding these two things together, it would become x plus, this would become 0 equals to 2. And that is 0 is our identity, right? Identity element. So we need to have identity because, any value plus identity element 0 would become itself. So then we get x equals to 2 because of that. So you see that for a very, basic equation that we want to solve, as I told you in an example, that the purpose for making groups was to, form them so that they can use different techniques to solve, the equations. So you need to have a basic definition so that you can solve simple things. If you add more rules over here, then you're kind of restricting that group into some unnecessary smaller, groups that you can find out there. But that was not the purpose. The purpose was to make them as general as possible so that they can cover more groups. But maybe this is an example that really opened up your eyes to see that, many years of hard working to find this small pieces together to define a group is something that passes all these things. And the reason that they chose this specific properties is that these are the properties that are essential to solve even a simple equation. So now that they have defined this group that they can solve the simple equations, then they can define groups to be elements could be geometric shapes, operation could be, I don't know, rotating the shape. It doesn't have to be a straight plus or addition. It could be like numbers that we are just talking about, and it could also be in a number theory that A lot of techniques they've used specific Gauss found to solve equations. So now they could use those because those techniques would work in a group, so it doesn't restrict it. So you can use that same technique to apply it on different groups. So that was the idea. If somebody finds a technique in geometric shapes, you can use that technique in solving equations, as long as they are both in a group. So that was the intuition, and now you start to understand that when we talk about groups, we are talking about the specific properties, and these are the minimum things we need to be able to have a group. All right. Now that we got this, let's move forward a little bit and find out why this become important in cryptography. So let's see when we do modular arithmetic, if you notice with some few examples that we've seen so far, it looked like we are going to use a lot of modular arithmetic. So if I am to do modular arithmetic, I really want to understand what is the difference between that versus the normal group of integers. I really want to have a good understanding over here. Okay, we have enough time to cover this too. So again, let me start with an example. So suppose that I have a set Z, and then I want to compare that one with the integers mod 5. All right, okay, we choose a number 5. I show a set of integers as, let's say this triangle, shows the set of numbers, elements in this group Z. And then when I do, take every element from this set Z, and I want you guys to see what this modular operation would do to this set Z, because all of them, there's no matter what modular operation, n that you do, it takes the Z and do something to it. So it would become very interesting to see that it would sort of partition the Z. So the first one would be the set of numbers that the remainder, when you do mod 5, you take any element in Z and you do mod 5, the remainder would become 0. And those sets are numbers such as this one. Minus 15, let me just write it very quickly, 10, minus 5, 0, 5, 10, 15, and so on and so forth, right? So if you see this integers, and they're coming from the set Z, the interesting thing about them is that if you do mod 5, they are multiples of 5, right? So the remainder would become always 0. So they would, take this portion of entire values in Z. There is another portion of numbers in this set Z that when you do mod 5, the remainder becomes 1. And if you think about those numbers, it would be minus 14, minus 9, minus 4, and it would be 1, 6, 11, and 16, and so on and so forth. And imagine this would be the portion of Z that covers those numbers. And then there would be again numbers that, the remainder would be 2 when you do mod, when you divide that number by 5. So that set would be the set of minus 13, minus 8, minus 3, 2, 8, 7, 12, and 17. And we continue this, okay, and then for the last one would be the group of numbers that their set is actually the remainder to 4. So it would be minus 11, minus 6, minus 1. It would be 4. It would be 9, 14, and then 19. So if you see over here closely, this would basically partition and cover all the numbers in Z. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then so on and so forth. So if you do the intersection of a union of all of them, then all of this would turn into the entire set Z. But what is interesting, when I wanted you guys to see, is that when you just apply this small operation, mod 5, this is basically what you're doing intuitively, is that you're partitioning the set Z into different sets. So now this small sets, we would start to give them names. So these would be the set of elements that we would denote them with brackets. 0, this would be with 1, this would be with 2, this would be with 3, and this one would be with 4. So what this set is saying is that this is a representative of all these elements. So any element you choose from the sets, the remainder of that integer to mod 5 would be 0. So these are what we call them residue classes. Residue classes. So the idea is that if you pick a number, any integer from this residue class of 1, and then you add it to another integer from the set of residue 2, then you always get an integer C from the residue class 3. That is very interesting, huh? Let's see what do we mean. You take an integer from this residue class 1. So let's say I pick 6, and I choose another integer from this residue class B. Let's say I choose 7. So when I do 6 plus 7, right, this would become 13. Mod 5, it is going to be 3, right? So it is going to be 13, but you see that 13 is in this group of 3, right? So we don't have to write 13, so we go back and write 3 because it is one of the residue, one of the elements in this residue class. So that is why when we are doing modular operations, no matter if any of this value from the set residue class 1, we choose any of them, and if you add it to any other element over here, we always get an element in this set 3, and we can just use this representative class. So then that means that Z mod 5 is going to be a set of a partition of residue classes that we can show them with the representative 1, 2, 3, and 4. Okay, so it is going to be the set of residue classes. Okay, so why did we do all these things? Because you're going to see this important property that you always saw it, but maybe it didn't really rhyme for you. So if we have A and B, if we have any two numbers in the same residue class, then we are going to say A is congruent with 3 strokes to B mod n. Let's be generic a bit, and then we read this loud as A is congruent to B mod n. This is how we read it loud. Let's see why is it so. What does it say? So, if I go back and see this example, like 11 and 16 are two elements that are both in residue class 1, which means that 11 mod 5 is 1 because 2 times 5 is 10. So the remainder is 1. And over here, 3 times 5 is 15. So the remainder is 1. So I know that 11 and 16 are in this residue class 1, right? Why is it so? Because 11 is congruent to 1 mod 5, and then 16 is also congruent to 1 mod 5. Then we are going to say, based on this, because they are the same class, then we are going to say 11 is congruent to 16 mod 5. I'm sorry, not mod 7. Right? So if you ever wondering that where this notation come from, like something is congruent to some other value, it is basically coming after this partitioning the set Z. So we are trying to say, if you pick two numbers that are coming from the same residue class, this operation is, congruent, is nothing but just saying that these values are coming from the same residue class, right? So I hope that this start to make more sense for you now. Any questions so far? Yeah, I will send you the PPT for this chapter soon, and also the previous chapter. I'll make the annotated one, and also the new chapter. You will soon be able to find it in EE class. I plan to send it before the class, but I just got some errors and I couldn't do that. But soon you will receive it. Okay, guys, I think we stop it here. The next thing that we want to go through would need more time, and we are almost out of time. So let me see one more time. Do we have any questions?
I remember you said at the start of the class that we have homework.
Right.
And yeah, do we have homework now? Because I didn't see on the E class, or I saw.
So whenever we get to
something
we cover the right amount that we can have a homework, I'll publish a homework. So, the moment that I publish it, you will receive an email, and then you can also go to EE class to download the homework, and then you have due time. So before the due time, you're required to upload the answers. Similarly, when we have midterm or when we would have final, so I will make an announcement. So again, you will receive an email that we will tell you when would be the midterm and how much it would be the coverage. So so far you haven't received any notification, just because we haven't covered enough. Normally I would have a set of homeworks right after maybe today, because we have covered the chapter 2. However, I can see that we have a little bit huge number of students in this class. So I sometimes try to merge the homework. So maybe I would wait for homework 1 and 2. I merge them together. So I just give you one homework. From a score perspective, it doesn't change anything, but it's just like it helps the TA a little bit more so that they can, do this correction a bit faster. So we would have combine 2 homeworks into one. So we would have 1 homework and 1 midterm, and then another homework with plus finals to check. So it is just a little bit of adjustment for logistic perspective, so that we can handle. We have almost more than 300 students registered in this class, so it becomes a bit challenging to cover all the things. All right. So since there's no question, see you guys next week. We will continue on this group, and yeah, I will upload the noted one into the EE class now. All right. Have a good day, guys.